Is everybody out there able to hear me and see me okay? Is good for now? Okay, good, good. We'll start in another minute or so here. Glad you guys are here tonight. And as always, thanks for those webcams. If you're able to be in a spot where you can turn one on, I really like that. I can at least make some visual contact with folks. That's always helpful. But yeah, it's about 6 o'clock. I think I'll go ahead and get started here tonight. We're going to warm up here in a minute with some review of those matrix algebra properties that we talked about last time. But before we do that, I just have a couple of announcements for everybody to be aware of. First of all, this is our last in Zoom lecture. So starting next week on Tuesday, in fact, over the weekend, I'm going to be coming back to Orange County. And so by next Tuesday, we'll be back in the classroom, which is McCarthy Hall 476. That's also on the syllabus if you need it. So I hope that you'll join me in person next week. I'm actually very eager to meet all of you guys, and it'll go much more smoothly. I do appreciate your patience with me during these first 2 weeks. It's been really nice for my parents to have me here to help them out as they've been recovering from their surgeries. But they're doing really great. I think they're going to be fine. And they've certainly given me their blessing to go ahead and get back to Cal State Fullerton in person. So yeah, that'll be starting next week. My office hours tonight and tomorrow night will be in Zoom only. So right after class, I have office hours at 8 o'clock all the way through the evening. And also on tomorrow night, I have office hours from 7 o'clock to 10 o'clock in the evening as well. There is homework due tomorrow night. I just wanted to remind you about that. It's your third assignment. It's still kind of the stuff from chapter 1. It's really important. The Bernoulli differential equations, the homogeneous differential equations of degree 0 that we've been talking about these last couple of classes. That's what you're getting some practice on with that homework assignment. I think there's also a couple of mixing problems with those chemicals pouring in and out of the tank. So that's also something worth practicing. So I think it's a really important homework assignment. And so I'm going to have a lot of office hours tonight and tomorrow night in case that might be of some use to you guys. As I said, I'll be coming back over the weekend. I will have Monday office hours that will be actually dual modality. So by Monday, I should be back to my office. So I'll still be doing all of my office hours in Zoom, every single office hour throughout the semester. But at least by Monday, I can also be in person. So if anybody wants to stop by early on Monday night, you certainly can do that as well. But yeah, so I'll be in transit for much of the weekend. Yeah, let me see. Oh, I also wanted to mention that next Tuesday is really important in terms of enrollment issues. If you are still on my waiting list, we need to make sure you get enrolled by next Tuesday. I think there's at least one person who was already sent an ad form yesterday and didn't yet use it. So make sure if the math department has contacted you through your regular email, that you make sure you use that ad permit and get yourself onto the roster, okay? If you don't get added by next Tuesday, then we have to go through a whole nother process of signing a bunch of forms. I think you have to pay a fee, and it just takes a big hassle. So let's try to get everybody added by Tuesday. The other thing is opposite issue. If there is anybody who is thinking they want to get out of here, that wouldn't be any of you guys, right? If anybody wants to withdraw from this class, I just want you to know that you can do it up until next Tuesday without even getting a W on your transcript. So it would be as if this never happened, right? So if you want to withdraw without a W showing up on your transcript, you do need to do that by Tuesday as well. So I'll remind you of this on Tuesday, that it's kind of the end of the line as far as adding and dropping. It becomes much more difficult after next Tuesday. I need to plug in my phone here. Sorry, 1 second. I had it unplugged. Can you guys still see me and hear me?
Yep.
Okay, great. I hope that my phone is charging now, so that I don't run out of juice here. Anyway, yeah, so that was the enrollment, the enrollment issues. I don't think I have any other announcements before we get into the math here tonight. Does anybody have any administrative type issues or questions for me?
I do have a question.
Go ahead.
So sorry if you already said something about it, I just didn't hear it.
Okay.
I know on the homework assignment tomorrow night, under required, there's obviously the problems and things like that, but there's a video as well. Do you want us to take notes on that and send it to you too?
Oh, I forgot about that. Yes, I just want you to watch the video. You don't have to send me the notes. The reason you don't have to send me the notes is that there's actually already a handout that goes with the video, and the handout actually has all the notes on it. So it would be really kind of redundant to make you do that. But I do want you to watch that video. It's only 7 minutes long, and it's really basic stuff. It's just something that I used to lecture on that in class, and it would chew up like 20 minutes, even though it's really only 7 minutes if I write a video about it, if I make a video. So it's just better to just have you watch that on your own. But thank you for bringing that to my attention. Yeah, good point. I'll try to remember to mention, it's kind of related to some of the stuff we're going to do right here. So I'll try to mention that as we get to that point. Anything else, guys, before we jump in tonight? As always, I just remind you, I do have my chat box open. So if you cannot use your microphone, or you just would rather type something in there, a question or a comment or anything, feel free to do that. I am kind of keeping one eye on the chat here as we go along. Yeah, by next week, we won't have to worry about any of that stuff. So that'll be nice. But on Tuesday, as you know, we kind of changed gears a little bit. And we started talking about linear algebra. Specifically, we jumped into chapter 2, and we were looking at systems of linear equations. And I said, hey, the main tool that we're going to use to study these is matrices. And so kind of towards the end of class on Tuesday, I ran through some of the properties or the operations that we can do on matrices, things like transposes or derivatives or integrals. We can do all that stuff. We can add, subtract, scalar multiply. We can do all these operations on matrices, right? And for the most part, all of that stuff is really straightforward. But I thought, just to kind of get the wheels turning this evening, I would just give you a little warm-up problem. This will be similar to some of the homework problems that you're going to see for next week on Tuesday. I should mention there will be an assignment due next Tuesday. It's a pretty short one. It's just got these kind of problems on it, but I do want everybody to practice this just a little bit to make sure that we can do it. So what do I have up here? I've got, I decided to just kind of randomly make up 3 matrices, as you can see. I'm calling them A, B, and C. And then I just want to do some calculations just to warm up. So it says, if possible, let's compute the quantity A transpose plus B times the quantity 2C. So right there, you see a lot of operations. There's a scalar multiplication. There's a plus sign. I see a transpose there. Actually, this is also a matrix multiplication. Let's start trying to fill in what some of these things are here. So just for the solution, I might just go ahead and fill in. I'm going to put an equal sign just to kind of get this started. Does everybody remember the transpose from last time? This is where you switch the rows and columns. You kind of swap them. So the first row of A would need to be written as a column in A transpose. So -2, 0, 1 comes down on the first column. And then the second row, which is 0, 1, and 3, gets written into the second column. And what we're going to do is add that to the matrix B. All right, well, we have the matrix B over here. It's on the board already. I'm just going to recopy that. And then we're going to multiply that So that's A transpose plus B. We're gonna multiply that by 2C. Now 2 is just a scalar, right? So we're just doing scalar multiplication. I'm actually gonna go ahead and double all of the entries of the matrix C. So I'll have a 2, a 0, a 6, and a 2. And then in the second row, -2, -4, 2, and 0. So we're just going to double all of the entries from the matrix C, and this is what we have to calculate, all right? Since we have parentheses around this first part, it would make sense, I think, to go ahead and do this addition first. And when you add matrices, we need to do it slot by slot. I talked about that last time. So I'm just going to add slot by slot here, and I'm gonna get a -1 and a 2 in the first row, and then a 1 and a 0 in the second row, and then a 2 and a 3 in the third row. That's my first matrix, and I still need to multiply that by the matrix on the right, which is, I'm just recopying it over here, 2, 0, 6, 2, and -2, -4, 2, and 0. So this is the matrix that we end up with, this matrix multiplication. Okay, so far so good? Pretty easy. The question I want to ask now is, can we do, because it does say compute if possible. Is this matrix multiplication possible to do? Let's look at the sizes of the matrices, because that's always the key, right? It's always the most important thing. What is the size of this first matrix here? You can use your, oh, I see a no and a yes in the chat. So we've got kind of almost a 50-50 vote on this one. What's the size of this first matrix here? 3 by 2, right? Yeah, Fabiola, that looks good. 3 rows, 2 columns, that's the first matrix. Okay, what about the size of the second matrix? Oh, some of you have already got that in there. 2 by 4, right? Yeah, so I'm taking a 3 by 2 matrix and I'm multiplying it by a 2 by 4 matrix. So is that allowed? Actually, that is allowed, right? As long as these numbers here, the columns of the first matrix is the same as the rows of the second matrix, then this is a yes. Yeah, we can actually do this one. So I am going to be able to calculate this. I'm going to try and squeeze it down here on the bottom of this board. The new matrix that we end up with is going to be what size? Is it going to be? Feel free to throw that in the chat as well. Yeah, 3 by 4. Okay, you guys are wide awake out there. I'm seeing lots of responses. So this one is going to be 3 by 4, which actually means there's 12 positions, right? 12 entries in this matrix. And the way we get those is by taking dot products. Remember from last time? We take rows of the first matrix and we dot them against columns of the second matrix. And we have 3 different rows and 4 different columns. That gives me 12 different ways to do this dot product. So I'm going to go ahead and do this fairly quickly with you right now. These dot products are pretty easy. -1 times 2, that's -2. And I add that to 2 times -2, which is -4. So that's -2 plus -4, which is actually -6 in the upper left corner, right? All right, then we move on, from there we move on over to the second column and we stick with the first row. First row dotted with the second column is 0 plus -8, right? And then first row dotted with the third column is -6 plus 4, which would be -2. All right, and then the last column, we dot that with the first row and we have -2 plus 0, which is just -2. Okay. Stop me if I'm getting anything wrong or going too fast. I can always slow down a little bit. When I get to the second row, I just want to show you a quick shortcut. Do you notice the second row is 1 and 0 here? When you dot 1, 0 with any other vector, you just pick off the first entry of that second vector. So actually the second row here is just going to be the same as the first row of the matrix on the right, 2, 0, 6, 2. Easy enough to just check that. And then finally for the bottom row, I have to do it slot by slot again with my dot product. So now I'm using 2, 3, and I'm dotting that with all 4 of those columns, right? So I'll have 2 plus -6, which is -2. and then I'll have 0 plus negative 12, which is negative 12. And then I'll have 12 plus 6, which is 18. And then I'll have 4 plus 0, which is 4. All right. That look okay to everybody? Hopefully I got everything right there. It's just basic addition and multiplication, and you're doing most of the time you do a lot of this in your head. So you just have to be a little bit careful with that. But that would be the answer. Okay, is that readable? Everybody can see that okay? Yeah, okay. Let me know if anything's unclear about that, all right? On my second board over here on the right, I have a second warm-up problem, which is to compute, actually this is the same matrices in the opposite order, right? So here you see on the second one, I want to do 2C on the left and then A transpose plus B on the right. So is that going to be possible on the second one? That's just my shorthand way of asking you what are the sizes of the matrices and does it work? So let's just check it out. 2C, we talked about that earlier. That was 2 by 4. And then A transpose plus B, that's 3 by 2, right? Well, the problem is these two numbers in the middle do not match, right? They are not the same. And whenever that happens, you can't do the matrix multiplication. So this one is actually not possible. That's not possible. Very good, very good. Yeah, Daniel, you make a good point there. A plus B is also not possible. If I wanted to add these two, just add these two original matrices here, you wouldn't be able to do it. They're not the same size. So you always have to be a little careful. Sometimes these things, you know, if you're not careful, you can end up making a mistake. So this is just a reminder of this property I mentioned at the end of class on Tuesday, which is that the order that you multiply matrices together in makes a difference. And we have to be very careful about that. So again, just to remind you one more time, this is worth writing down a couple of times because this is a big deal in the world of matrix algebra. In general, if you multiply two matrices A and B together, it will give you a different answer than if you multiplied them in the opposite order. Okay, so we're gonna always be very careful about that, right? We're gonna make sure we don't switch the order of something. Sometimes it can be subtle, and you really have to be focused in on it to make sure that you don't make a mistake with that. Okay, any questions on these little warm-up exercises? I just wanted to kind of get us warmed up for the evening here. Okay, great. In that case, I'm going to just give you a few more basics about matrix algebra, and then eventually, by the time we get a little later into our class tonight, the main focus is going to be going back to linear systems of equations and learning how to solve them. So that's definitely something that's coming up. But I just want to give you a few more, sort of foundational points here. I'm going to start with another definition. If the matrix A is n by n, then we call A. So if it has the same number of rows and columns, right? If the n and the m are actually the same number, then we call A square matrix. Then we call A a square matrix, and that's because it looks like the shape of a square. If it has the same number of rows and columns, then visually it should look like the shape of a square. If you have a square matrix, then there are some very special kinds of square matrices. They might be symmetric, they might be skew symmetric, they might be triangular, they might be diagonal. This is what that 7-minute video is about that is in Canvas for you to watch. I'm gonna let you do that. There's some notes that I've already written up about this that are also in Canvas. So I'll probably send an email reminder to just do that. Again, this is not part of an assignment that you have to worry about, but you do need to watch. I'm going to expect everybody to know what a symmetric matrix is, what an upper triangular matrix is. And so that 7-minute video will explain all of that. And those concepts really only apply to a square matrix. Okay, so this type of matrix, it turns out, it comes up a lot, and it's really very important. Let me write down 2 other matrices that are also really important. These I will record right here. These are also in that video, but I'm just going to go ahead and add them right now. 2 important matrices here. The first one is the so-called zero matrix. And the zero matrix, it doesn't get much easier than this, guys. This is just a matrix where every single entry is just 0, right? So this is going to be written as 0 sub m by n. So if you see that notation, 0 with an m by n next to it, then that just means it's a matrix that's just filled with all zeros of that size, m by n. Now, if the matrix is actually a square matrix, then we might just abbreviate that as 0 sub n, and we may not write, I mean, if you wrote n by n, that would be okay, but sometimes it's abbreviated to this. And just to warn you, mathematicians really like to take advantage of context. And so what I mean by that is sometimes for a matrix, they'll just write 0, and it looks like it's a number. But in fact, because of the context or whatever the situation is that you're working in, it's not literally the number 0 here. That 0 could, in fact, be just a sort of a sloppy shorthand for the 0 matrix that, again, I will try not to do that to you very often. I'll usually try to make sure it's clear whether I'm looking at a number or a matrix or whatever. But I just want you to know that out there in the real world, people get kind of lazy and they just kind of write 0 down, and you're supposed to just know that, oh, that's a matrix 0. That's not the number 0. Anyway, so this is just the 0 matrix, and you'll see that get used from time to time. Now, the second one, which is only slightly more involved, is this so-called identity matrix. So let me say a word about that as well. Identity matrix, and this one has to be a square matrix. So the notation that is adopted pretty standard in our book, and you'll see it most of the time, is I sub n. Again, somebody might get lazy and just write I, and you would need to know what that is. What is this identity matrix? Well, it's an n by n matrix, so it should look like a square shape. It should be a square matrix. And how is it filled out? Well, it is filled out with ones kind of going down this diagonal of this matrix. When you have a square matrix like this, guys, there's actually sort of a notion of the main diagonal of that matrix, sort of starting in the upper left corner here and going down and to the right to the far bottom right corner. This is called the main diagonal of the matrix. Again, in my 7-minute video, I briefly talk about this. The rest of the entries, both above and below that main diagonal, are all just 0. Okay, so this is a matrix that also has a lot of zeros in it, but it has ones on that main diagonal. And it turns out that the effect of that, like why is this matrix important? Well, it turns out, and I'll just show you an example. If you take the identity matrix, let's just use I2 for an example here. And let's just say you multiply it by some matrix A. So I'm going to write down my 2 by 2 identity matrix. So it's going to look like 1 and 0, and then 0 and 1. And then what I'm going to do, guys, is I'm just going to imagine that A is just any old 2 by 2 matrix here. So we might have any old 2 by 2 matrix. If you do this multiplication, so again, using the dot product matrix multiplication scheme, so you go across the rows of the first matrix and you dot those with the columns of the second matrix. If you do that, my friends, what actually ends up happening is you just end up getting the second matrix back again. You end up getting A, B, C, D out of that. Okay, these dot products are all really very minor because you have ones and zeros primarily that you're using in the calculation. So just check it out. If you just do the matrix multiplication, that's what you get. So you end up getting the matrix A, whatever A was, that's what you have, okay? You end up just getting A. So if you take the identity matrix, right? If you take I and you multiply it by anything else, it just leaves it alone. So it sort of behaves like the number 1 does under multiplication. If I take 1 times any other number, I just get that other number back again, right? Nothing changes. That's the same thing here. If I take the identity matrix and I multiply it by any other matrix, I just get that other matrix back again, right? And actually, I should point out, I mentioned that you have to get lucky for 2 matrices to commute with each other. It turns out the identity matrix does actually commute with everybody. So this would be the same result. I'll just add this over here, guys. If I multiply by the identity matrix on the right, so if I did it like this and I put that identity matrix on the right, you can check it. You can check the matrix multiplication. It will work. You'll get A times I2. Right? So this is one case where you kind of win the lottery. You take 2 matrices and you want to know, do they commute? Well, if one of the matrices is the identity matrix, then those matrices will commute actually, and you've gotten lucky. Because as I said Tuesday, most of the time, if you just grab 2 matrices at random and you multiply them in both orders, very, very unlikely that they would give you the same answer. But if one of those matrices is this identity matrix, then it actually does work. You do get the commutativity to work in that case. Okay, so far so good. Any questions here, guys? Okay, so I want to write down a few more properties about matrix algebra here for you. And none of this is going to be terribly exciting, but I just feel, for the record, I just want to get them written down, and then we'll move on. Okay. Give myself a little more room here. I am going to be glad to be back in a regular classroom, I think. Yeah, so let's make a list of some matrix properties. And there's going to be actually 10 things in this list. It's going to be a fairly long list that I'm about to make. So save enough room for yourself wherever you're taking notes so you can write these all down. I'm going to need, to express these properties, I'm going to need as many as 3 matrices. So I'm just going to say let A, B, and C. So let A, B, C be matrices of compatible sizes. A, B, and C matrices of compatible sizes. What I mean by that is, okay, if the sizes don't match up, then we get another one of these not possible outcomes, right? So I just like to assume that everything is possible, okay? Make sure that the matrices have sizes that are compatible with the operations that we're talking about, okay? So with that, I'm going to now make a list here of some properties, and there's going to be 10 of them. And most of these are not all that interesting. Take the first one, for example. The first property just says if you take any matrix A, which is M by N, and you add the 0 matrix to it, remember this is the 0 matrix, it's M by N size, and it's got all zeros in it. If you add a matrix of all zeros to whatever you started with, guess what? I know this is shocking. You get the same matrix back again, right? So that's equal to A again. Very, very exciting. Okay, so that's the first property. The second one is also very exciting. If we take the scalar 0 and we multiply it by any matrix A, again, A is M by N, So you take this matrix and you do scalar multiplication here. Remember guys, scalar multiplication is just done slot by slot. So you're literally multiplying that 0 into each and every entry of the matrix. And guess what's going to happen? You're just going to zero out every single slot of that matrix. This is just going to be the zero matrix of whatever that size was, m by n. Okay, so that's certainly not surprising either. Let's do one that's a little more interesting. The third property here is, I'm actually going to use all three matrices, A, B, and C this time. It turns out if you want to take A times B times C, if you want to multiply all of these together, A, B, and C, if I put parentheses around the AB and I calculate that first and then multiply the result with C, it's actually the same as if you started by doing the simplification of BC and then pre-multiplying it by A. Keep in mind here, guys, that I have not changed the order that the matrices appear in, right? A is first, B is second, and C is third on both sides of this equation, right? So that's important to preserve. But what this is really saying, guys, is that parentheses don't matter. Parentheses don't matter. I can put the matrices in any, I mean, I could just ignore the parentheses altogether. So if I wrote down ABC, that would be fine. We wouldn't need the parentheses to clarify it because order of parentheses doesn't matter. Okay, that's all we're saying. Actually, to prove this is quite a whirlwind. It's done in the book for any of you who are interested in it, but I will tell you, it's just a lot of mumbo jumbo notation that is kind of technical, and it's not hard math. And I don't find it to be very enlightening, and you don't learn a lot from doing it, and it takes a great deal of patience. I'm not going to do that with you here. We're just going to kind of accept this fact. It's pretty reasonable. It's pretty reasonable. So we'll leave it at that. That's the third property. Okay, let's keep going here. By the way, I still have my eyes on the chat, so if I'm going too fast or you have a question as we keep talking, I hope that you'll all stop and let me know. The next one is the distributive law. In fact, I got two of these. So the first one is if I take A times the quantity B plus C, that can be written as AB plus AC. So you just distribute exactly as you would expect. Notice I'm not changing the order of anything though, right? I'm being careful not to violate this commutativity problem over here. And I can do the distributive law also with the addition in front. So I could have A plus B times C. And again, you literally just distribute this exactly as you would in any other algebra, high school algebra type of class, right? So that's pretty straightforward as well. Okay. All right. The next one here is let's make sure I'm getting everything I want. Yeah. The next one here is if I take a matrix A, let's say it's m by n, and I multiply it by the n by n identity matrix. I kind of already talked about this, didn't I? The identity matrix is like multiplying by 1. It really doesn't affect the answer at all. So that's just going to be equal to A. All right. Number 7, I'm going to separate this out as a separate item because I'm going to multiply on the left by the identity matrix. And the only thing I have to point out here, guys, is that if I put the identity matrix on the left side, it needs to be I sub m in order for it to make sense, right? So remember, the number of columns of the first matrix has to match the number of rows of the second matrix. So for this to make sense, with the identity matrix in front, it has to be I sub m. But assuming we do that, we still get the same result. Identity matrix acts like multiplying by 1. All right? So that's this matrix over here. This is a really important matrix in linear algebra, and it's going to be showing up a lot in what we're going to be doing. So here's a couple of properties that kind of remind us why at least one reason why this identity matrix is so important. Okay, excellent. I have just 3 more properties to go. The last 3 have to do with transpose. Okay, so I'm going to keep going here. 8, 9, and 10. Maybe you guys can help me with number 8. What would happen if I took a matrix A and I transposed it? Remember, transpose means I'm going to swap the rows and the columns, right? I switch the rows and the columns. What if I do that and then I transpose the result again? What do you suppose we're going to end up with? You can use your chat box if you want. Just curious. If I take the transpose of A, yeah, you guys are all over it. You're just going to get back to what you started with, right? That's just going to be A again. Absolutely right. Love it. I love it. That looks really good. Okay. What about this one? Here's number 9. What if I have 2 matrices A and B and I add them together and then I decide after that I want to transpose the result? Is there any other way that we could maybe do that calculation? If you have an idea, go ahead and put it in the chat while I'm erasing a little bit here. Then I'll check that out and we'll see where everybody's at on this. It's sort of like, does flipping rows and columns have any problem with adding the numbers? Like if I add the numbers first and then do the transpose, which is what this is, right? Would it be any different than if I transposed the individual matrices separately and then added the results? I personally think, as it looks like many of you do, that we should just end up with the same result. So that's exactly right. This is just A transpose plus B transpose. That's exactly right. Okay, no surprise there. Okay, and then one last one here that I want to write down as well is going to be the transpose of A times B this time. And get this erased a little bit better. Any thoughts on maybe what that should be equal to? You can use the chat or your microphone, I don't care. Any gut feelings about that? Ooh, it's gotten a little quiet around here. Oh, there's A transpose times B transpose. That's starting to come through. Okay. There was a little hesitation out there. I think I want to pause for a minute. I'm going to show you on my other board over here, because it turns out that what you guys are coming up with in the chat, which is what most people would think of, turns out it's not correct. Oh, I can't believe that. Let me show you something. Let's just come over here and just scribble on my sideboard for a minute. Let's suppose that A was M by N. And then let's suppose that B was N by P. So this is kind of the normal dimensions that I've been using to talk about matrix multiplication. So if I start off like that, then A times B would be M by P, right? In terms of the size of it. And then if I transpose that, okay, you don't necessarily have to write all of this down. I just kind of want to scribble here for a second. If I transpose that, I'll be switching the P and the M. So I'll end up with something that's got a size of P by M, right? So what happens if I look at the individual transposes? Right, so if I come over here and I do A transpose, this is going to be N by M. And then B transpose is going to be P by N. So I have a question. Can I even do A transpose times B transpose? Just again, kind of remembering how the size thing works for matrix multiplication is kind of a problem, isn't it? Right, this doesn't even work because the M and the P are not the same necessarily here, right? So we can't actually do that. The question becomes, what can we do? Like, what can we do that would make sense? And I think I saw Daniel with it in the chat a minute ago, which is the thing that we could do. So A transpose, B transpose, this one is not possible. But what is possible, guys, is B transpose A transpose, right? So P by N times N by M, that would actually be P by M again. The size would actually be correct now. And it turns out that that is how the formula is supposed to go. So this is going to be B transpose times A transpose. So here again, we're in another situation where the order that we write the matrices down in really is very important. So if you see something like this again, which I'm pretty sure we will, make sure you remember to switch the order of the A and the B on this transpose property. It's a little bit quirky, but that turns out to be correct now, the way I've got it there. Okay, so that one throws a little surprise at us here, kind of at the end of our list, but the rest of the list is pretty much just exactly what you would expect. There's nothing weird about any of these other properties here. I just want to stop and check. Are there any questions about any of this? So far, so good. All right, fantastic. Well, guys, this is kind of the end of this first part of what I wanted to do tonight. And so far, I've kind of, if those of you trying to follow along with the book, I've kind of covered the first 3 sections of chapter 2 in kind of a whirlwind fashion, kind of jumped around a little bit, I spit most of it out fairly quickly because it is relatively background material. Your homework assignment for next Tuesday is just on these first 3 sections. So I've kind of covered all of that already. But what I want to spend most of tonight on, or the rest of tonight on, is I want to go back now to the linear systems of equations. And I want to talk about how we can use matrices to try to solve them. Remember on Tuesday, I said that the big goal of chapter 2 is to solve systems of equations. And I said that we're going to use matrices as a tool to do that. But then I've gone off on this big side tangent about matrices, right? I really want to get back to, all right, how do we actually use matrices to solve those systems? So we're gonna spend most of the rest of tonight focusing on that. And that is really where sections 2.4 and 2.5 come in. So that's what I want to get to now, unless there's any sort of leftover questions here so far. So far, so good. All right, I hope I haven't bored you too much. The first part of chapter 2 is always a little slow. But now we're going to really get into why this is also useful and a little bit more of the concepts here, which I think hopefully everybody's going to appreciate this. So I'm going to jump into section 2.4. Now I'm really lining back up with the book again. And the title I'm going to give for this little section is EROs and REFs. Okay. Those are acronyms for some words that we need to use for this conversation. And in a few minutes, you'll know what EROs means and you'll know what REFs means. Okay, so for right now, what I want to start with is 3 remarks. So I'm going to make 3 observations here. And these are going to take a little bit of time. So these are actually kind of the important things for us to pay attention to here. So let me start off with this first remark, okay? The first remark, and this is about linear systems of equations, right? So a linear system is easy to solve. A linear system is easy to solve by this so-called back substitution. A linear system is easy to solve by back substitution. Just kind of underline that to emphasize it. If it is in a so-called, I'll put this in quotes, triangular form. if it's in a so-called triangular form. In this case, it's actually very easy to solve a linear system. Let me show you an example so you'll know what I mean by triangular form. So there's an easy example we can write down immediately for this. I'm gonna write down a linear system that's in triangular form, and then we'll see if we can solve it, because this says it's easy to do it. Okay, let's just check it out. My first equation in the system, it's gonna be 2x minus 3y plus z equals 6. And then my second equation is 4y minus z equals 8. And then my third equation is going to be z equals 4. Okay, so there is a linear system, right? That's a system. We've got three unknowns here, which are x, y, and z. And why is this called triangular, by the way? Well, if you kind of look at the left side, you can kind of see a triangle here. If you kind of shape the equations, you can see there's some empty spaces that allow us to kind of draw that like a triangle. So that's what I mean by this so-called triangular form. But do you see that I can solve this one really easily for the unknowns? If you start at the bottom, z is equal to 4. I already know that. And then I could take that value and I could back substitute it into the previous equation. Now, if I do that, let me just put the results over here. I hope this is readable. You see, if I go back to the middle equation and I put in z equals 4, I can solve for y. And I'm doing this kind of in my head real quick. If I solve for y, it should be equal to 3, right? All right, and so I know that y is equal to 3. I know that z is equal to 4. So now I can take both of those values and go back to the first equation where I'm going to now solve for x, right? So I can solve for x. Let me just, again, I'll just squeeze this in over here. When I solve this for x, it's a little bit of work, but it's not hard. The answer turns out to be 11 over 2. I had lots of time before class to get this right. So x is 11 over 2 in this case. So wasn't that easy, right? It says it's going to be easy to do it, and we now know what x is, we know what y is, and we know what z is. So I think I've illustrated my point. A linear system is easy to solve if it's in triangular form. Now, by the way, while I'm on the topic of solving this system, I want to start getting some good habits out of everyone right away, which is that this is not going to be a good way to write our answer. We've kind of done a bunch of chicken scratch mental calculations, and we've just got x, y, and z kind of sitting over there on the side. What I'm really going to want you to do, and we're really talking about like 2 homework assignments from now when you're actually working on this, but I'm going to want you to present your solution set in a more formal way. So I'm going to write that here so you can see how it would look. For the solution set, I want you to use braces like this. So and inside of the braces, we're going to write down the solutions, but let's make sure we put the variables in the same order that they're in our system. So the x comes first. That was 11 over 2. Then we have y, which was 3. So we do 11 over 2, comma, 3, and then comma, 4. And then we end our parentheses and we end our braces. So this is the way you would then, like this would be the answer I would want you to circle on your paper, right? It has the final answer in it. Okay, so this tells me what x, y, and z are, and I've got my solution set. Okay, everybody comfortable so far? So if the system is in triangular form, then it's easy to solve it by back substitution. That's my first remark. Okay, let me go on to the second remark if we're all ready for that. Number 2 here. Number 2. What this says is no solutions. No solutions. Let me come over here so I can write a little bit easier. No solutions are gained. No solutions are gained or lost if we perform if we perform these so-called elementary row operations. No solutions are gained or lost if we perform these elementary row operations. So I have to explain what I mean here. I'm not done with this remark. I just want to give myself some room. Okay. By the way, elementary starts with an E, row starts with an R, operations starts with an O. EROs. The title of this section is EROs and REFs. And anytime you hear me say EROs, I'm talking about elementary row operations. And it turns out there are 3 of them. And I'm going to write them down for you guys now. And then we'll see, hopefully this will all make sense and you guys will understand why my remark applies here. Okay, so here's the first one. I'm going to label these with A, B, and C. So the first ERO is a permute. So this is the word permute, 2 equations. Okay, so we can permute 2 equations. When we're doing EROs, guys, I'm going to want us to keep track, do some bookkeeping about what those EROs were. So I have a notation for you. I'm going to want you to write this when you're doing these kinds of EROs. A PIJ, P sub ij, like that. That is the way we can write down that we are permuting the ith and the jth equation. Okay, so just so you guys understand what I'm talking about, let's go back to this example that we had over here. You don't need to write this down. I just kind of want you to see this and believe it. Let's say that I chose to take the system over here on the right, the example that we were just solving, and I write it down like this. Let's say I write it down like that. Now, it's the same 3 equations that we had over in our example on the other board. But what I have done here is I have permuted the second and third equation, which I'm going to write this way. P23 is what I've done here. My question is the solution to the system any different now than it was before? Have I gained any solutions? Have I lost any solutions? Not at all, right? I have not lost anything out of this. The only thing that I would say is that, it doesn't look like a triangle anymore. On the left side, it doesn't really look like a triangle anymore, right? Let's imagine that I started you off with the system looking like this. What my remark says here is that I can switch these last 2 rows and rewrite it like that in the triangular form that's then easy to solve, you see. Is everybody kind of getting the spirit of what we're going to do? We're going to take our system, whatever it is, and we're going to perform these EROs on it. And we're going to know that that's safe, by the way. Nothing will be gained or lost if we do that. We're going to perform EROs on it to try to get it into this triangular form. This is the whole idea. Anyway, so that's one ERO. Let me write down another one. Oh, actually, I'm going to keep this up. Let me keep this up here for just another minute. Sorry. So let's do part B right here. The second ERO. This one is multiply. Multiply the ith equation. Multiply the ith equation through by some constant, which I'm going to call k, as long as that constant is not 0. Okay, so I can multiply an equation through by a non-zero constant k. And my notation for this ERO is going to be the following. m sub I of k. Okay, so you'll see me use that notation. It just means I'm gonna multiply one of my equations through by a constant. And I'm pretty sure you guys will agree that nothing will be gained or lost if I do that. Take this system down here. If I take this equation z equals 4 and I decide to multiply that equation through by 10, so I multiply the second equation through by 10, now I've got 10z equals 40. Has anything changed? Not at all, right? Not at all. Z is still equal to 4, y is still equal to 3, and x is still equal to 11 over 2, right? We still have the same solution set that we did in the original form that we had the problem, okay? So nothing has been gained or lost by that. Okay, one more ERO here. This is probably the one that we use the most, and it's also a little bit tricky. So we'll practice all of this, don't worry. But this one is called adding. So we are going to add this time. And what is it? It's k times the ith equation. We're going to add k times the ith equation to the jth equation. We're going to add k times the ith equation to the jth equation. And there's a notation for that as well, which is aij of k. All right? aij of k. A sub ij of k. Right. Guys, if you've seen another book on linear algebra, you might have seen some different notations for these. I really want you to try to use my notations here. We have them for a reason. I do think they're the best choice that we could make here. But yeah, that is the third ERO that we have. We can take one of our equations and we can do mental math on it. I'm going to multiply it in my head by k and add that to another equation. I want to point out that in this ERO, the ith equation actually does not change. The equation that feels the effect of this ERO is actually the jth one. We're taking a multiple of the ith one and we're forcing it to be added on to the jth equation. The jth equation is the one that changes, not the ith one. We're simply using the ith one to implement this change to the jth equation. That turns out, maybe it's not quite as obvious to you guys, but it also turns out to be a safe thing to do to a linear system. We will not gain or lose anything as a result. Okay? So that is my second remark. It's a little long-winded, right? These EROs are safe. That's really what it says. And in a few minutes, we'll get a chance to practice these EROs on a real example, okay? Before I do another example though, I want to get my third remark in. It says 3 remarks over there. This third remark is just a quick one, so this won't take but a minute. And what this just says on number 3, guys, is that the 1 and 2 above, the first 2 remarks, right, they can be applied. They can be applied to the rows of a matrix. It's probably going to be, if it's a linear system, it's going to be some augmented matrix. I'm going to write it as A sharp here. They can be applied to the rows of A sharp. So when you read the way I phrased A, B, and C, I'm talking about equations. Multiply an equation by a constant, add a multiple of one equation to another. But see, the first thing you're going to do with your system of linear equations, you're going to put them into a matrix, right? You're going to make a matrix out of them. And then what you're really going to be doing is you're going to be applying these EROs onto the rows of that matrix. It's going to be the A sharp where you're doing all of the work. Again, I'm going to do an example in just a few minutes here to show you that. All right. So I hope that I'm making some sense out there. Now I still see some people nodding. Okay, that's good. Once in a while, a little positive feedback is great. I really appreciate that. What I want to now just summarize again, I've already kind of said this, but I just want to kind of give you again the big picture of this process that we're sort of trying to develop right now, which is that we are going to use EROs to convert. We're going to use EROs to convert this A-sharp matrix into, well, you probably assume that I'm going to write triangular form there. Because after all, that was the first remark, is let's do EROs and get this matrix into a form that's easy to solve by back substitution. Here's the problem though. The matrix is not always going to look like a triangle. The system is not always going to look like a triangle. Here I was able to kind of make sense of that on this example, but if my matrix had only, if my system had only 2 equations and there were like 75 unknowns, this isn't going to look like a triangle. Mathematicians don't want to use kind of this misleading casual word for this. So there's a fancier name for what we're going to convert A-sharp into. It's not triangular form. Rather, it is something called row echelon form. Row echelon form. That's what we're going to do. Okay, it's just a fancy word for the triangular form. The word row starts with an R. The word echelon starts with an E. The word form starts with an F. In other words, this is REF, and that's the other part of the title of this section. Row echelon form is often abbreviated with REF. That's exactly right. So what I'm going to do, guys, we're going to take a break shortly. But just before I take a break, I just want to write down what a row echelon form really is required to look like. And then we'll, after we take a little break, we'll come back and do an example to practice this whole thing. Okay, I know there's a lot of information up here, and we're going to be doing a lot of this, so I definitely want to practice it. But let me, before we take a little break, let's just get the definition down. So I've got it on my board before we go any further. Okay, so yeah, I think I can erase all of this for now. We don't really need any of this at this point. So let me put this definition down, guys, and let's see if this makes sense. So I'm gonna just give a definition of row echelon form right now. Okay, so here it is. A matrix is in row echelon form if there's just two requirements here. There's just 2 rules. The first one is any all 0 rows. So if there's any rows that are just all 0 all the way across, any all 0 rows, they should be at the bottom. So these are at the bottom. So if I have any rows that are all zeros, they should be at the bottom of this row echelon form. What if it's not? What if I have a row of zeros that's not at the bottom of the matrix right now? What do you suppose I'm gonna probably try to do? You can use the chat or use your microphone. I'm just asking, what if I have a row of zeros and I don't have it at the bottom of the matrix the way I want to? We have, of course, these EROs that we can work with. Oh, okay, now my chat is catching up. A lot of people writing the word permute into their chat. Exactly right, that is one of our EROs. We can permute that row of zeros down to the bottom. That's exactly the way we would try to do that, okay? So we can certainly make that happen. That's not too bad, okay? So that's the first thing. And then the second thing is that for all other rows, the first non-zero entry So there'll be a non-zero entry, right, in any other row, and there's a name for this while I'm at it. I'll just tell you what this is. This is called a pivot. So a pivot is just the first non-zero entry in a row of a matrix. It must be a 1. Okay, I'm gonna stop again. I'm still not done, but I wanna stop again. What if I look at a particular row and the first non-zero entry is a 7? All right, what am I gonna do if the first non-zero entry in my row is a 7? Okay, I see a couple of answers here in the chat coming through. I don't like to use the word divide because if you look at what the EROs are, we're supposed to be doing either a permute or a multiply or an add. Of course, when you say divide by 7, I see a couple people have that. That's the same thing, right, as multiplying by 1/7. That's exactly right. You could multiply by like whatever the reciprocal of that first non-zero number is. So yeah, so we can certainly arrange this, right? We can certainly make this pivot into a 1. And then there's one more thing we have to require here, which is, I'm gonna add this here, and occurs to the right of the pivot. It occurs to the right of the pivot in the row above. Okay, so the pivots actually have to go kind of down and to the right. Yeah, that's really the point here. Let me just kind of sketch out for you what that would look like. I'm going to put it over here actually, just so I can have this all in one place on this one board. Just so you see a visual of this, I'll draw this and then we'll take a little break, okay? So what I might have for a row echelon form of a matrix is I might have something that looks like this. So here's my matrix, right? If there's a row of all zeros, it needs to be down here at the bottom. So I could just, let's say there's a couple of those. So it could be something like this, right? So you just have any rows of all zeros goes to the bottom. And then in all of the other rows, we have to start with a pivot first, which should be a 1. So I'm gonna put a 1 right there in the upper left corner. The numbers that are after the pivots can be anything. So I'm just putting little stars there. I hope that's visible on your screen. The stars just means that numbers could be anything. We don't have to worry about that at all. But the first one should be a 1. And then in the next row down, the pivot has to be to the right of this pivot. So there might be, it could be several zeros, and then we get to another pivot again. It could be something like that. Okay, so 0, 0, 0, and then we get to a pivot. Again, to the right of my pivots, any numbers could go. It doesn't really matter. And then maybe there's another row, and again, the pivots have to go further to the right each time we go down to one row below. Not every column has to have a pivot. So in this little example, the second and third columns, there was no pivot there at all, okay? But where there are pivots, they do need to go down and to the right. Does this make sense? You might notice that I put little diamonds on those pivots there. You often will not see that. If you look at linear algebra books, they won't do that. But I'm going to tell you guys, I cannot overemphasize this enough. The positions of the pivots in these matrices, which by the way, this is not going to be a passing thought. We're going to be doing this process that we're learning tonight for the next 10 weeks. So we've got to get the hang of it. And what I often find is that people don't appreciate just enough how crucial the pivot positions are. So I'm not really requiring you to like put diamonds or circles around your pivots, but I'm going to strongly, strongly, strongly recommend it because it just helps you keep things straight in your mind and visually helps you understand what's going on. So I will be doing that. You're going to see lots of diamonds going around these pivot positions. when I'm writing things down. And I really encourage you in the strongest possible terms to do the same thing. I'm not going to take off points if you don't do it, but boy, you're kind of setting yourself up much better if you circle those pivots. I promise you'll be thanking me for that suggestion at some point. Okay, if there's no questions for right now, guys, I am ready to take a 10-minute break. It's just a hair before 7:10, so in about 10 minutes, I guess that'll be about 7:20 or so, we will have a half hour to go, and I'm going to actually do a couple of examples of this ERO process, okay? So take a break from the screen if you'd like, grab some water, stretch your legs, and I'll see you back here in 10 minutes. Well, guys, if you're out there somewhere within the sound of my voice, in about another minute or so, I am going to start back in again and pick things up. So this is a good time to find your way back over here, and we'll just do this last half hour. All right, guys, I think I'm going to go ahead and get back to it here. Just 30 more minutes of this, and then next week we'll be back in person and have a whole lot more whiteboard space to work with, and hopefully it'll be a whole lot better for you. Yeah, the main thing I want to do in this last half hour is really practice some of the ideas we've just been talking about. We wrote down those 3 remarks, and they are intended for a purpose that it's going to help us to solve linear systems. And so before we actually look at an actual linear system, I just want to practice the EROs once, because this in and of itself already is maybe something that takes a little bit of focus to get the hang of. So I put an example on my board over here during the break. Hopefully everybody can read this example okay, because this is actually what we're going to start with here. I've got a matrix A, and it's got 3 rows and 4 columns, as you can see. And what I want to do is find a row echelon form for A. Okay, so we're going to try to find a row echelon form for this matrix. I've kind of on the left side, I've reminded you kind of what the form of this row echelon form should look like roughly. And yeah, we're going to do those EROs. It's really the process that we talked about a little bit ago. We're going to perform EROs to bring this matrix into row echelon form. Okay, so let's get started. I'll mostly solve the problem probably over here on this side. And so the way we're going to do this, guys, we're going to start with the matrix A, which is what was given to us. And we're going to try to do some EROs. Now, I want us, especially in the beginning of learning how to do this, I want you to write down what EROs you're using. And a good way to kind of do this is to use this little sideways S, which is called a twiddle. This is a little twiddle symbol. Every time you write down a little twiddle, it tells me that you're doing an ERO. All right. Can somebody suggest, now keeping in mind that we need to get a 1 into the upper left corner of our row echelon form, can somebody suggest with the matrix that I gave you over here, what's a good way or a good ERO that we could use that would bring a 1 into that upper left corner? Go ahead and put it in the chat or use your microphone, either way.
You can swap the second or third row to the top row.
Exactly. I just want to do a permute, and I see several people in the chat also suggesting the same thing. That sounds great to me. So what I'm going to do here is I'm going to do P12. I'll just go ahead and permute the first 2 rows. I want to see that on your homework papers. By the way, this will be homework for, like, this is 2 assignments from now. But anyway, we're learning it right now. So we're going to switch the first 2 rows. So now the second row goes to the top, and the top row goes to the middle, right? We're not doing anything else. We're just permuting the first 2 rows. The third row just stays the same. We don't have to make any changes there. I'm going to circle this pivot now, though, because in the upper left corner of the matrix, I have a 1, which is great. That is a pivot. Okay. It's somewhere along about now where sometimes people get a little confused about what they should do next. The really important thing, guys, is to make sure that the pivots below the first row are moved over to the right. You see, the pivots have to go down and to the right. In order for that to happen, you actually have to have zeros below your pivot. Do you see that over here? Below your pivot, all zeros. Below this pivot, all zeros. Below any pivot, you need to have all zeros. So what I'm going to suggest is we're not going to mess around with the first row at all. But can somebody suggest how I could get a zero right there in that second row below that pivot that we've established? We have 3 operations that we can use. Hugo, you've got to use my notation. Okay, sorry. I need you to use, it sounds like you're taking rows and subtracting them or adding them. I want you to talk about either permute or multiply or add. So Daniel has adding negative row 2 to row 3. I actually, yeah, let's fix that. We can do this, guys, actually very easily. I can actually just do, all I have to do, guys, to figure out what ERO to use, everybody listening to this, all I have to do is look at these 2 numbers. These 2 numbers. I can use the 1 and the 2. I don't have to use the third row at all, right? Just those first 2 numbers in that first column. To use that, I can use that 1 to zero out the 2 that's below it. And the way I do that is I use the add operation. I'm going to add, so here it comes, guys. A1, 2. I'm going to add with rows 1 and 2. And what is the multiplier? I'm going to take negative 2. So I'm going to put of negative 2 here. A1, 2 of negative 2. Let's just remember, what does this mean? Can everybody see this here? No, I'm sitting in front of it. Add negative 2 times the first row to the second row. So I'm going to go all the way across the first row, and in my head, I'm not going to write it down. I'm just going to mentally multiply everything in that first row by negative 2, and then I'm going to add that to the second row. I'm not changing the first row at all. I'm just using the first row to add some multiple of it to the second row. So in this case, if I take negative 2 times 1 and I add that to 2, it becomes 0. If I take negative 2 times negative 2 and add that to negative 1, it becomes 3. If I take negative 2 times 1 and add that to 3, I get 1. And if I take negative 2 times 3 and add that to 4, I get negative 2. Okay, most of this is happening in my head, right? I don't write anything down. I don't, I just wait till I've actually done the multiplication and adding to the second row in this case. Okay, so that's how I'm going to get a 0 right there. Does everybody understand that step? That's actually like the one we use the most, that step. Now, here's another thing. I could just, again, I haven't done anything about the third row yet, but you know what you can do to save time? We can actually go ahead and work on getting a 0 here in the same step, right? So I'm wondering, using my A notation, can you guys in your chat boxes tell me what operation or what numbers with this A notation would help me to get a 0 down there in the bottom left corner? Let's just see if anybody's understanding this A thing here. Yeah, okay. I'm seeing some good signs here. I have A1, 3. That means I'm using the first row with the third row. And I'm going to take the negative 1 of the first row and add it to the third row. How do I know that that's the right thing to do? Well, because I have a 1 here and a 1 here. And how do I use a 1 to cancel out a 1? I take negative of it to add it to 1. So I am going to also, at the same time, guys, I am going to do A1, 3 of negative 1. That's going to add the negative of the first row to the third row. And I'll get 0, negative 3, negative 1, and 2. It's going to look just like so. Okay, great. Is everybody good with that? So now here's where we're at. And I'm wondering, does somebody want to suggest, maybe at this point we're ready to go on to another step. Maybe anybody have a suggestion what they'd like me to do at this point with this matrix? By the way, the first row is good. Let's not go back to the first row again. Okay, I could multiply the second row by 1/3. I see a couple of people in the chat suggesting that. So that would be M2 of 1/3. And in doing that, I'm not changing the first row at all. So I'll just recopy that. I take 1/3 times the second row. Okay, so this is what I will have, a 0, a 1, a 1/3, and a -2/3. And then I'm leaving the third row exactly the same as well, okay? And I can actually circle this pivot now as well. In the second row, we have a 1 as our first non-zero entry, and that means that that is a pivot. Okay, great. And then I think we need another step still, because it's not quite in row echelon form yet. I need to get a 0 below this pivot in the second column. I need to get a 0 here. Does anybody have a suggestion what ERO would accomplish that? You can use the chat or your microphone, either way. I want to get a 0 right here. Because below that pivot, I have to have a 0. Okay, A23, I've got a couple people in the chat at least brave enough to give it a try. Yeah, A23 of 3, I love it. Very good, guys. A23 of 3, let's write that down. What does that mean again? That means I'm taking 3 times the second row and adding it to the third row. So what that's going to do is the following. I'm going to leave the first row the same. I'm going to leave the second row the same. And I'm going to take 3 times the second row and add that to the third row, which actually is going to completely zero that row out. All zeros on the bottom row, which is good because we remember that the row echelon form should have all 0 rows on the bottom. Guys, this is it. This is row echelon form. Looks good to me. Okay. I like it. Let me clear this off so I can make a couple of comments here about this before we go on to another example. I have just a few general remarks about this, and these are actually pretty important, but I may not write it all down. It's kind of more just, just common sense kind of stuff. You notice how I did do 2 EROs at once right here in one step? Be careful not to go hog wild with that. If I decided that I wanted to permute 2 equations, and then also at the same time I was going to multiply one of them through by 5, and then also at the same time I was going to add 3 times this equation to the other equation, you can see how quickly this gets confusing, especially when you're doing it all in your head half the time, right? So the thing about the 2 that I did together here is that they were both the same kind of ERO, and they did not sort of interfere with each other in any way whatsoever. If you were to permute 2 rows and then say, oh, I also want to multiply the first row by 3, then I'm going to have to stop and ask you, well, do you mean the first row before you permuted it or after you permuted it, right? It'll become unclear to me, I think, like what order did you do these EROs in, and then how could you possibly keep this all straight in your head? So try your best, guys, not to go hog wild on like combining too many steps together at once. Something like this, though, is really safe. Okay, that's comment number 1. I won't bother to write that one down. That's more just like a heads up as you're doing these problems. This next one is maybe is worth a little bit more of a written comment, which is, do you think that this is the only right answer that we could have had? I'm pretty much in agreement with the chat folks who are all saying no. You know, we could have started in the very first step. I said, how do I get a 1 into the upper left corner? We could have started with this matrix and we could have said, hey, let's just multiply the first row by 1/2. And if we had done that, we would have gotten our 1 in that upper left corner. And that first row would then be filled, by the way, with fractions. Does that sound like fun to do EROs with fractions? Not so much. Not so much, guys. Do your best. Here we did end up with some fractions eventually, but not until almost the end. You're going to hate doing these problems if you set up EROs that create fractions right away. I promise you that on the homework, right, you shouldn't need to have like pages and pages of fractions and doing EROs with fractions, adding multiples of one fraction row to another fraction row, which sounds like a nightmare, right? Try not to introduce fractions unless you really have to, or if you're almost at the end of the process. Okay, so yeah, but if we had done that, right? If we had multiplied the first row by 1/2, then we would have ended up with a first row that's already looking different from what we have here, right? And so that suggests that we would potentially have many right answers. And I want to make that remark into the notes here as well. So let me add this remark here, because I think this one is worth writing down. The row echelon form of a matrix A is not unique. Many correct answers are possible. Many correct answers might very well be possible. In fact, we've got what, 35 people in this room approximately. We could have 35 different answers, okay? Fadi's asking me, could it happen that we would not reach all zeros at the last row? It turns out, no, you would have to get all zeros in the last row. I'm gonna comment on this in just a minute. Guys, this is a double-edged sword. This is really nice because it means lots of us can have right answers. They can all be correct and everything else. I love that. There is a downside to it. Do any of you like to check your answers in the back of the book? It's kind of nice, right? But the problem is that if there's a million correct answers, the back of the book is only going to show you one of them. So if you go to the back of the book with your row echelon form and it's not the same as what's in the back of the book, it actually does not mean that your answer is wrong, because there can be many correct answers and they're just not all in the book. You can't do it, right? There's literally infinitely many of them. So in terms of checking answers, this is not such a great remark for us, but it is just the way it is. There can be many correct answers. Now, somebody in my first class asked me about this thing called reduced row echelon form. You might see this if you're really looking carefully in the book. There is something called reduced row echelon form for a matrix, and that is unique. There is only one right answer for that. However, I'm not going to go here. Turns out the extra work that you have to do to get your matrix into this sort of higher level of reduced row echelon form is usually not worth the effort compared to what you get out of it. And so I'm not going to talk about reduced row echelon form in this class. You can read it in the book if you're interested. It basically just means that you want to have zeros above and below all of your pivots, not just below them, but both above and below them. We don't need that here. It's not really so critical. And so let's not worry about that. But we do have to accept that if we're working with a row echelon form, it may not be unique. And we can have as many different correct answers as there are people in this room. However, okay, there is a silver lining. And I'm going to write this one down. However, there is one thing about every correct row echelon form in common. There is one thing that they would all share in common. And this gets back to what Fadi was asking about in the chat. There is one thing that every correct answer would have to have, and that is the number of pivots. The number of pivots. And this is so important in linear algebra that I have to give it to you as another definition. Okay, it is called the rank of the matrix A. This number, this rank, is just equal to the number of pivots the number of pivots in any row echelon form. So every row echelon form at least has to agree about that point. So if you check your answer in the back of the book and the number of pivots in the book's answer is not the same as the number of pivots that you came up with, that's a little bit of a red flag. At that point, we have to be concerned maybe our answer is not correct, because that is supposed to be unique about a matrix, that we would always have the same number of pivots. And Fadi, number of pivots is of course directly related to, did you have rows of zeros? Because the rows of zeros don't have pivots in them. All of the others do. So you can kind of make that connection directly from that. Okay, so this rank is a unique quantity. In our example above, in the example that we just did over here on the other board, what is the rank of that matrix then? How many pivots do I have? Yeah, I've got them circled, remember? Circling the pivots is always a great idea, because that helps me to find those important parts of my row echelon form. So yeah, this matrix has rank 2. By the way, you usually cannot tell what the rank is just by looking at the original matrix. Right, I look at the original matrix, I've got 3 rows. So I can't tell whether there's going to be 1 pivot, 2 pivots, 3 pivots, whatever, just by glancing at it. We really have to get down in the weeds here. We have to do these EROs, get that row echelon form, and then we will know what the rank is. This is a hugely important concept in linear algebra. So we're going to be talking about ranks of matrices all semester long. Okay? Any questions on this example here, guys? Okay, if not, we've only got 10 minutes left. I'm just going to, in this example, there was no system of equations that we were trying to solve. It was just sort of a straight matrix. I want to set up one more example where there's actually a system of equations, so you can start to see how it's going to play out. I may not finish this example fully right now, but we can at least get it started, and then we can come back to it next time. Okay, so let me come back over here and do one more example, and then we'll call it a night. When we sort of implement this process, guys, which is to take our system of equations and solve it by using the process of EROs, bringing the matrix into row echelon form, there is a name for this. It's actually the title of the next section of the book, so I'm going to start this right now. Again, we only have a few minutes. I will not finish this right now, but I at least want to start so that we have a place to begin next week, kind of already having a little bit of an idea of what's going on. This is called Gaussian elimination. And this is the name for this technique that we're talking about right now. Okay, and there is no better way to help you guys understand what Gaussian elimination is than to show you an example. So I'm going to at least start an example here. And the example is going to be to just solve this system that I'm going to write down, and I'm not going to make it too easy, by the way. It's going to be a little bit complicated. So here's the system: 2u minus 3v plus w minus x plus y equals 0. Okay, and then my second equation is going to be 4u minus 6v plus 2w minus 3x minus y equals -5. And then there's one more equation, -2u plus 3v minus 2w plus 2x minus y equals 3. Okay. The goal here is to solve for the unknowns. I probably should say, if possible. As we've learned that sometimes you can't solve a system, but I'll just leave it like this. This one turns out it will have a solution. But the goal here is to find out what are U, V, W, X, and Y. Those are the unknowns of the system, okay? So the solution to that, the running joke of 250B is that every problem, you solve it by throwing it into a matrix. So that's exactly what I'm gonna do right now. I am going to build, this time it's actually the augmented matrix, A sharp. So I will be keeping track of this right-hand side vector. So let's just copy all of the coefficients, 2, -3, 1, -1, 1, and then we're augmenting that. And remember, I like to use a bar to separate out that right-hand column, augmenting that with 0. And then for the second row, we will do the second coefficients. So 4, -6, 2, -3, -1, and -5. And then for the last row, -2, 3, -2, 2, -1, and then augmented with 3. So the first thing to do, we don't have to really think too hard, we just write down the matrix, okay? The unknowns do not get written down in the matrix, right? You don't see them there, but we should always remember that they are lined up with these columns. Oops, that's not X, that's U. So there's the U column, there's the V column, there's the W column, there's the X column, and then there's the Y column. I like to remind myself that, yeah, these unknowns, they are in the background here, but in terms of the matrix itself, we don't write them into the matrix, okay? So far, so good. Yeah, so now I'm gonna do my EROs again, okay? And we're running a little short on time, so I think instead of like doing a straw poll of everybody out there, I'm just gonna kind of tell you what would be maybe a good set of steps to do. I would not start by multiplying through by 1/2 on the first row, because that would create a ton of fractions right at the beginning. And I don't want to see those fractions too early, because then I'm going to have to live with those fractions through all of the calculations that follow. If we were doing this class on a computer and the computer was doing all of the adding of fractions and stuff, maybe it would be okay. But this is mostly going to be by hand that we're doing all of this, right? By the way, I should mention before I go any further, this type of stuff, especially when you're first learning it, try not to do it like when you're really tired at night. Try not to do it when you're distracted by a television or other people or anything like that, because honestly, it's so easy to make a little mistake on these EROs. And you can imagine, right? As soon as there's one little mistake, that mistake gets sort of promulgated all the way through the rest of your work, and it just makes things worse. And by the time you get done, you're like, oh my gosh, this is horrible. So you really want to do this when you're able to focus on it. The flip side of that coin is I've seen a lot of students who they do make mistakes and end up with the wrong answers on these row echelon form calculations. But I know, and they know, that they know it really well. Like they understand how to do it, which is really what I care about, right? So if you miscopy a number somewhere, or if you do a little mental calculation in your head wrong, please don't take that to mean that, oh, I must not understand this, right? That's just, anybody could do that. I probably will do it sometime. One of you is going to bail me out, right? So it's easy to have those kinds of typos in this work. So just my suggestion is, don't do this when you're, make sure you eat your Wheaties before you go in and start working on these ERO problems, okay? Anyway, I would not start with a 1/2 here. I would start, I'm gonna go right here. I'm gonna start with A12 of -2. Okay, so I'm gonna leave the first row the same. Okay, I'm gonna leave the first row exactly the same as it was before, but I'm gonna take -2 times the first row, and I'm gonna add that to the second row, and you can see why. You can see why, guys, the 2 and the 4, right? That's all I'm looking at. I'm not looking at anything over to the right. I'm just looking in this first column. I have a 2 and a 4. I want to turn that 4 into a 0. So I'm going to do A12 of -2. And if I do that all the way across the entire matrix, I'll get 0, 0, 0, -1, -3, and -5. There you go. That's the second row. And then at the same time, I'm gonna try to get a 0 down here as well in the bottom row. To accomplish that, I'm only going to look at the 2 and the -2 from that first column, and I'm gonna say, how do I use a 2 to cancel a -2? I just add the 2 to the -2. So I'm also going to do A13 of 1. This is just adding the first row to the third row. So 0, 0, -1, 1, 0, and 3. That's what we would have. I'm gonna go ahead and circle where the pivots are as of this moment. Even though they're not technically pivots yet, I wanna kind of visually see where they are. And are they arranged correctly right now? They're supposed to go down and to the right. Right now, I don't have them like that. So what operation would I want to use here to get them going kind of down into the, let's get the positions cleaned up first. What operation would allow me to get this going down and to the right? Yeah, Tien, Daniel, Wesley, great job. Yeah, we're just going to permute the second and third rows, right? So I'm just going to do P2, 3. Okay, so the first row, again, just stays the same. First row stays the same. But I'm now going to permute the second row to the third row and the third row to the second row. Just recopying the exact same numbers, but just switching the 2 rows. And now I'll circle those pivot positions one more time here. And I'm pretty happy with the positions of those pivots at this point. The positions of those pivots looks really good. The only thing wrong with this is that the pivots are supposed to be 1s, right? So I can make that happen by just multiplying the rows through by the reciprocals of those pivots. So we only have a minute left, but that's about all I'm gonna need here. I am going to multiply the first row by 1/2. At the same time, I'm gonna multiply the second row by -1. And I'm gonna multiply the third row by -1. I'm gonna just take the reciprocals of all 3 rows. And when I do that, the first row, now we're getting all the fractions, right? But see, I don't mind getting the fractions now. At this point, I don't mind it at all. I wouldn't have wanted it at the beginning, but now we're basically done. So I'm gonna go ahead and use those fractions. The second row, we need a minus sign. So minus sign puts that to be a 1, and then a -1, a 0, and a -3. I'm almost done, guys. Just give me one more minute here. And then the third row, I also have to pick up a minus sign. I'll get a 1, a 3, and a 5. This is my row echelon form for this matrix. In this case, the rank is 3, right? We have 3 pivots, 1 in each of the rows of the matrix. This is the so-called triangular form that is supposed to be easy to solve by back substitution. However, this one's kind of a bit more mucky than the simple one that I gave you in the first part of our class. And I don't have time to show you right now how we actually do that. So I am going to keep you guys in suspense for 5 days. Do you think you can handle it? 5 days from now, and it will be in person too. 5 days from now, I'm probably going to come in next Tuesday and put this example back on the board again. I won't recopy it all. I'll probably go straight to this row echelon form at the end. But I need to show you how to do the back substitution when you've got this kind of a weird shape of a matrix, because it doesn't really look clear how the back substitution works from here. So let's save that. We don't need that for this weekend. You guys can focus on the other stuff we've done this week. And yeah, I don't have anything else for tonight. I'm going to go over to my office hours shortly. If you have questions on the homework, feel free to stop by either tonight or tomorrow night for my office hours. But I really, really appreciate you guys these 2 weeks letting me do this through Zoom. It's been really helpful for my family, but I am really excited to see you guys soon. So stay safe this weekend, take care of yourselves, and I will see you next time. That's it for now. Bye, everyone.
I got a quick question real quick on this super fast.
You bet, no worries.
So on this step 2, where there's 2 additions, and step 4, where there's 3 multiplications,
Yes,
it would be the same thing if you just split those up into multiple steps, right? Or does it only work that exact way like that?
no, it would be, you could split it up into three steps, you would have more steps total written
Okay.
down, and so it would take more writing.
Just
So I'm
whatever you're
trying to
willing to
help
do.
people save a little writing by doing it this way, but it's not required. You
Got
don't have to combine them together.
Cool.
Yeah, good point.
Thank you.
You're welcome.